Okay, if you've ever written a line of code, you've definitely seen that angry red squiggle telling you you're missing a closing bracket. But have you ever stopped to wonder, how does the computer actually know that? Today, we're going to pull back the curtain on the theory of computation to see how machines really learn to read.
So yeah, that's the big question, isn't it? For you and me, looking at a line of code and seeing matching parentheses is pretty easy. But imagine you're the computer. You can only read one character at a time, in a straight line. How on earth do you keep track of all those nested layers?
I mean, look at a simple expression like this. Our brains just get it. We see the y plus z is wrapped up, and then the whole thing is wrapped up. But for a simple machine, this is a serious headache. It sees the first parentheses, and it has to somehow remember it's waiting for a matching partner later on. How does it do that? To figure that out, let's start at the beginning, with the most basic kind of machine. And as you're about to see, for our specific problem, it's got a pretty massive flaw.
This little guy is a Nondeterministic Finite Automaton, or an NFA for short. The best way to think about it is that it's a machine that can explore every possibility at once. When it's a fork in the road, it basically sends out clones of itself down every path to see if any of them work out. Super flexible, but it's missing one absolutely critical piece.
And here's the fatal flaw. The NFA has zero memory. It has no idea what it saw a millisecond ago. It only knows the state it's in right now. So trying to match parentheses with an NFA, it's like trying to bake a cake, but your recipe self-destructs after you read each line. You can't do it. It's impossible.
So, if the problem is a lack of memory, the solution is kind of obvious, right? We've got to give our machine an upgrade. We need to give it a memory.
Okay, this is probably the simplest and best way to picture the difference. A basic finite automaton is like a person trying to follow complex instructions with no way to write anything down. But a pushdown automaton, or a PDA, is that same person, but now they have a notebook. And in computer science, we call that notebook a stack. And what's so cool is how this one tiny addition changes the entire game. A PDA is really just an NFA plus a stack. That's it. But this stack gives it the power to remember things in a very specific way. The last thing you write down is the first thing you look at. And as it turns out, that's the perfect kind of memory for our problem.
So how does it actually use this notebook? Well, it's a simple little three-step dance. First, it reads the next character in the code. Second, it peeks at the very top note in its notebook. And third, based on a set of rules, it decides to either add a new note to the top, that's a push, or tear the top note off, that's a pop.
And boom, we're right back at our parenthesis problem. When the PDA sees an open parenthesis, it just pushes it onto the stack. It jots it down in its notebook. Then, when it finally sees a closed parenthesis, it pops the matching one off the stack. It crosses it off the list. If the notebook is empty at the very end, success. Everything is perfectly balanced. Okay, deep breaths. This looks like a bunch of scary math homework, I know, but don't worry. This is really just a formal academic way of listing out all the parts we've already been talking about. It's just a list of its possible states, the letters it's allowed to read, the letters it can write in its notebook, its rulebook, where it starts and which states count as a win. That's all it is. Now remember that whole sending out clones idea from the simple machine? Well, PDAs can do that too. They can be non-deterministic, meaning sometimes they have to essentially guess which rule to follow. And for some really complex languages, this isn't just a neat trick, it's absolutely essential. The machine wouldn't work without it. All right, so we've built our awesome new machine with a memory. It's ready to go. But a machine is useless if it doesn't have any instructions, right? How does it know the rules for a language like Python or Java? Well, it needs a blueprint.
And that blueprint is called a context-free grammar, or CFG. You can think of a CFG as the official rulebook for a language's syntax. It describes every single valid structure you can build. And trust me, every compiler for every major programming language you've ever used has one of these at its very core.
So this grammar has four basic parts. You've got terminals, which are the actual characters themselves, like a plus sign or the number 5. Then you have non-terminals, which are like abstract concepts or placeholders, like expression. Then you have the production rules, which tell you how to swap out those placeholders. And finally, a start symbol to get the whole process going. Let's look at a super simple example to make this real. These rules say that an expression can be another expression plus a term, or an expression can just be a term all by itself. And a term can be any of these numbers. See how that works? Using just these few rules, you can start to build all sorts of valid math statements. So let's say you have a string of code.
And you have the grammar. How do you prove that your code actually follows the rules? You build what's called a parse tree. It's the visual proof, the evidence that connects your concrete line of code all the way back to the abstract rules of the language.
And this isn't just some theoretical exercise. This is literally what a compiler does to understand your code. It takes a line like this, builds this exact tree structure, and uses it to confirm that, yep, this is a valid expression according to the blueprint. This is the moment your code goes from being just text to being understood.
Okay, we've covered the machine and we've covered its blueprint. Now, for our final section, let's just zoom out and see where our pushdown automaton fits into the grand scheme of things.
This table pretty much says it all. You can think of it as a ladder of computational power. Down at the bottom, you have the memoryless finite automata, which can only recognize really simple languages. Take one step up, and you've got our hero, the pushdown automation. That single notebook, that one stack, lets it understand much more complex things like programming languages. And at the very top, you have the legendary Turing Machine with basically infinite memory.
So, if you take one thing away from this whole explainer, let it be this. The story of computation is really the story of memory. More memory equals more power. Every step up that ladder is just giving the machine a better way to remember things, which directly unlocks its ability to understand more and more complex ideas.
And I'll leave you with this final kind of mind-bending thought. We know a PDA with one stack is powerful, but it's still limited. But, and get this, if you give that same machine a second stack, it suddenly becomes just as powerful as a Turing machine. It can solve any computable problem. So why do you think that is? Why does adding just one more notebook suddenly unlock the entire universe of computation? It's a pretty wild thing to think about. Thanks for joining me.